All right, let's just jump right in, shall we? Today, we're tackling one of the all-time classic coding questions, trapping rainwater. Now, I know that can sound a little intimidating, but I want you to picture it less like some scary algorithm and more like a really fun visual puzzle that we're going to crack together. So, what's the actual problem we're solving here? Well, it's actually beautifully simple. Just imagine a cityscape, a skyline of buildings of different heights. After a huge downpour, water gets trapped in the gaps between the taller buildings. Our mission, should we choose to accept it, is to figure out exactly how much water is stuck in there. And this kicks off our quest for efficiency, starting with the most obvious way to do it. So, first up, let's meet our first contender in this puzzle. We're going to call this approach the brute. And just like its name suggests, this method is all about raw power. It's straightforward, it'll get the job done. But, as you're about to see, it's not exactly the most elegant solution in the world. So how does this brute actually think? Well, the logic is super straightforward, really. For every, and I mean every, single bar in our city-state, it stops. And it asks two simple questions. What's the absolute tallest building to my left, and what's the absolute tallest building to my right? See, the water can only fill up to the height of the shorter of those two walls. So we figure that out, subtract the height of the bar we're currently on, and boom, that's how much water is trapped right there. Then we just do that for all the other bars and add it all up. So what's the verdict on the brute? Well, the great thing is, it's really easy to get your head around. But, and this is a huge but, it is slow. Painfully slow. Because we're rescanning the left and right sides for every single bar, it just grinds to a halt when the cityscape gets bigger. We call this O of n squared time complexity, which is just a technical way of saying it's not really practical for anything big. Okay, so the brute force method works. It gets us the right answer. But man, is it a workout. This brings us to the big question. Can we solve this puzzle without doing all of that repetitive work over and over again? There has to be a smarter way, right?
And the answer is, of course we can. So let's bring in our next solution, which we'll call the strategist. This one's a lot cleverer. It uses a key idea from dynamic programming, which basically says, if you find yourself doing the same calculation over and over, why not just, do it once and write down the answer for later?
And that's the whole key right there. Don't repeat your work. Instead of running around looking for the tallest bar to the left and the tallest bar to the right for every single position, what if we just figured all that out one time, up front? We can pre-calculate all this info and just store it. Okay, so here's part one of the strategy. We're going to create a new list. Let's call it left max. And all we do is walk across our cityscape one time, just once, from left to right. At every building, we just jot down the tallest building we've seen so far. By the time we get to the end, we have this perfect little cheat sheet with all the left max values.
You can probably guess what's next, right? We do the exact same thing, but this time from the other direction. We make another list, right max, and we walk from right to left, again, just keeping track of the tallest building we've seen so far. And just like that, our strategist has two complete cheat sheets. No more rescanning necessary.
And what do we get for all this pre-planning? A huge speed boost. We've gone from that slow O of n squared to O of n, which is just way, way faster. But, and there's almost always a but, right? There's a trade-off. We had to create 2 extra lists to hold our data, which means we're using up more memory. It's a fantastic improvement, for sure, but it does make you wonder, can we get that speed without using all that extra space? And that brings us to our grand finale, the most elegant, the most efficient, and honestly, the cleverest solution of them all. Let's call this one the Ninja. It's fast, it's sleek, and it accomplishes its mission without leaving a trace, meaning it uses no extra memory. This is the real master-level approach. So, how does the Ninja operate? The setup couldn't be simpler. Imagine this. We put one pointer at the very start of our buildings and another one at the very, very end. That's it. Now they're just going to start walking towards each other, destined to meet in the middle. Now, this whole trick, this whole beautiful solution hangs on one single brilliant insight, and it's this. The amount of water you can trap at any point is always limited by whichever wall around you is shorter. Think about it. You don't need to know the absolute tallest wall on the right if you already know your left wall is tiny. That tiny left wall is what sets the water level, period. So here's how the dance works. At every single step, we just look at the building under our left pointer and the building under our right pointer. If the building on the left is shorter, we can confidently calculate the trapped water right there. Why? Because we know for a fact there's an even taller wall somewhere to the right holding the water in. So we do the math and then just nudge the left pointer one step closer to the middle. If the right building's shorter, we do the exact same logic, but for the right side. And we just keep doing this little dance until the pointers finally meet. It's absolutely brilliant.
All right, so we've seen 3 totally different ways to crack this puzzle. We had the brute, all about pure muscle, the strategist, who is clever and planned ahead, and the ninja, the silent, efficient master. Let's put them side by side for the final verdict.
Okay, let's just lay it all out. The brute, simple to understand but way too slow. The strategist, fast, which is great, but it was a memory hog. And then there's the ninja. The 2-pointer approach. It gives us everything we want. It's super fast, O of n, and it uses practically no extra memory, what we call O of 1. It is, hands down, the champion.
You know, at the end of the day, this whole thing isn't just about finding an answer. It's really about the journey of finding the best answer. And that's why this problem is so classic. It's the perfect example of how just shifting your perspective a little bit can unlock a solution that's not just better, but way more elegant and powerful. So I want to leave you with this thought. This whole 2-pointer technique, this ninja way of thinking, it's not just for this one problem. It's a super powerful tool you can use all over the place. So the real question to ask yourself is, what other tricky puzzles out there could you solve with this clever technique?